Hello guys, welcome back to my channel Gamma Rai Gamma. Now, million apologies for not uh, uploading my Laplace transform for differential equations part 2 video soon, but here it is on the great occasion of Halloween. Happy Halloween, first of all. Now, if you haven't watched the first video, please watch it because otherwise this one's gonna be just mumbo jumbo if you don't know the concepts. Let's get started. Okay, this video is all about the applications of Laplace transform in differential equations. So, the simplest differential equation we encounter is the case of the simple harmonic oscillator in simple harmonic motion. Physics majors will know this pretty well. So we get this by having Newton's second law, F equals ma. Our acceleration can be written as the second derivative of displacement with respect to time, and the restoring force given by Hooke's law, which is negative kx. Now we're going to forget the coefficients of m and k and deal with just the simple differential equation. Second derivative of y with respect to time is equal to negative y. I just dropped the coefficients. The form of the differential equation is similar. Now, the way I'm going to look at this problem is that if I pull this block to the right so that the spring is extended by a delta y value, and then when I leave it from this point, it will just start oscillating back and forth and back and forth and back and forth. And I want to write equations with respect to this reference point. So our equations will basically start predicting the motion of this block from the reference point y equals 0. So I can set the condition that the displacement at t equals 0 is 0 because I want to start from this reference point. That's the first constraint. The second constraint is, when I start whatever, like I leave the block from here and then it comes back to the reference point, it will have a certain velocity. So the first derivative of y at time t equals 0, let's call that 1, say 1 meter per second velocity. That's the second constraint. Okay, now we know the constraints. Let's take the Laplace transform on both sides. When I do that, and if I hope you watched the second video, the first video, the video before this one, we have s squared Laplace of y minus s times y at t equals 0 minus first derivative of y at t equals 0 is equal to negative Laplace of y. Now I'm just going to use different notation. I'm going to call Laplace of y to be capital Y of s. The output is s by the convention of Laplace transforms. So we have s squared y of s. This will go to 0 because of the first constraint, minus this will become 1 because of the second constraint, is equal to negative y of s. Now rearranging some terms, we get y of s times s squared plus 1 is equal to 1. Have y of s equal 1 over s squared plus 1. Y of s was Laplace of y. So if we take inverse Laplace on both sides, we're just going to get y. So we need to take the inverse Laplace of capital Y of s. So when I do that, you look at the table of Laplace transforms or inverse Laplace transform, you get y now, because of applying the inverse Laplace, is equal to the sine of t. Why t? Because we originally had everything in terms of t, right? The y was a function of t. So, and this perfectly fits the behavior of this system. It's the if you check the graph and the displacement of this, it's both of them have a periodic nature, appropriate periodic nature. Now if we just modify our constraints a little bit, if we say that initially, well, change the constraint, say displacement at time t equals 0 is L, because now we want to measure from this reference point, this second reference point. But at that time the first derivative of y is 0, because we're assuming it starts from rest at that point at least. So then if I just write everything again, this differential equation again, I have s squared y of s minus s times L, the first derivative term goes away, is equal to negative y of s. Again, grouping terms, we have SL. Y of s is s over s squared plus 1 multiplied with this arbitrary constant L. Now take the inverse Laplace on both sides. So the L is a constant which will come outside. If you check your table again, this is cosine of t. This is a y. So I mean, the essence of this solution, the solution to this differential equation is trigonometric terms like sine and cosine are going to satisfy a differential equation of this form given the appropriate initial conditions. Because you slightly change the initial conditions, a sine becomes a cosine, and stuff like that. I mean, since this differential equation is linear, you can have any linear combinations of this cosine and this sine, and that will still be a solution to the differential equation just because it's linear. Okay, I think it's time to grow up a little, I don't care about second order differential equations. Let's move on to third order differential equations. And these are pretty hard to solve. So we have this differential equation here and the constraints. So y at 0 is 1. First derivative of y at 0 is negative 1. Second derivative of y at 0 is 0. Fine. Just take the Laplace of y triple prime plus 3y double prime plus 3y prime plus y and the Laplace of 0. Now the third derivative using the formula we derived in the first video will become s cubed Laplace of y, which is capital Y of s, minus s squared y of 0 minus s times first derivative of y at 0 minus second derivative of y at 0. That's the y triple prime term. Now the double prime term will have a 3 multiplied 3 s squared capital Y of s minus 3s y at 0 minus 3 first derivative of y at 0 plus 3s. Now this is the y single prime term. 3s times capital Y of s minus 3 times y of 0 plus capital Y of s. That's the capital Y of s is this single y term is equal to 0. Now, using these constraints and like cancelling out the terms, especially the second derivative terms, we can simplify stuff even further and just make y of s the subject of the equation to get s squared plus 2s divided by s cubed plus 3s squared plus 3s plus 1. Now I would like to add and subtract 1 in the numerator. I have s squared plus 2s plus 1 minus 1 divided by s cubed plus 3s squared plus 3s plus 1. We can split this up as s squared plus 2s plus 1 over s cubed plus 3s squared plus 3s plus 1 minus 1 over s cubed plus 3s squared plus 3s plus 1. Now notice the numerator is just s plus 1 but the whole thing squared over s plus 1 the whole thing cubed minus 1 over s plus 1 cubed. That was our capital Y of s. Take the inverse Laplace now. So the first term is just 1 over s plus 1, which will just be e to the negative t by the shifting theorem, minus t squared over 2 and e to the negative t again by the shifting theorem. That is small y. And that indeed is a solution to the differential equation. Now mind you, now the factorization here was pretty easy because I chose constraints like that. Every time it may not be easy, and sometimes even the inverse Laplace transforms would be non-elementary, or it would be really hard to find, or you have to use some special identities or theorems like convolution theorem or like other formulas. So just it is a powerful technique if you have a clear idea of where you're coming from and where you're going. So just keep that in mind. Now one thing I should tell you about using Laplace transform for differential equations is it may not work every time. And here's an excellent example of that. Well, say you have a big mass m, a small mass small m at some arbitrary distance x from the mass, and the Newtonian gravitational force is given by g, universal gravitational constant, capital M small m over the distance of separation squared between them. And if we equate that to Newton's second law equation, F is equal to ma. Now acceleration is the second derivative of displacement with respect to time. And if we equate both of them, m times second derivative of x with respect to time is equal to g times capital M small m over x squared. The small m will cancel off, giving a second derivative of x with respect to time is just gm over x squared. Now since this is a second order differential equation, you may be tempted to take the Laplace transform on both sides. If we do that, the left hand side will be pretty standard, s squared y of s minus s times y of 0 minus first derivative of y at 0 is equal to gm is a constant, the Laplace of 1 over x squared, or x to the negative 2 power. Well, the issue here is that the Laplace of a negative power is not defined, because the Laplace of a power, I think, if I remember the formula correct, say Laplace of say t to the n was just s to the n plus 1 over the gamma of n plus 1. And we have a negative 2 for n. So we'll have a s to negative 1 over gamma of negative 1. Now the gamma function is very poorly defined over negative numbers. So this we will have a problem here. That's why we can't use Laplace transform. However fitting the form of the differential equation might be, we need to basically use other techniques like substitution, like basically converting into velocity, or using the time independent energy principles in physics to tackle such problems. And I'm sure it's, apart from Laplace transform, there are excellent methods of solving such type of systems, like as I said, substitution is one example. So just, if I'm teaching you a method, I will teach you its drawbacks so that you're never baffled by why it doesn't work and when it doesn't work. Now, just to conclude this discussion of Laplace transforms, in the first video I had Laplace transform of derivatives. In the second video, which is this video, let's do a Laplace transform of an integral. So we have Laplace transform of integral from 0 to t, and since we already used t, let's have a dummy variable tau, f of tau d tau. So just use the definition of Laplace transform. E to the negative st, integral from 0 to t, f of tau d tau dt. Now we can use integration by parts here. I would like to anti-differentiate this while I differentiate this under the integral sign. This will be e to the negative st over negative s, the first, this guy as it is, integral from 0 to t, f of tau d tau. But all of this entire express, the first term, evaluated from t tends to infinity and t is equal to 0, minus minus plus e to the negative st over s, and we have plus e to the negative st over s, and the derivative with respect to t of this second term, integral from 0 to t, f of tau d tau, evaluated, actually we don't need to evaluate that because it's inside an integral from 0 to infinity of basically dt. Just erase this line part. That's why, just be careful while writing this stuff. Okay, so when t is infinity, the first term, we'll have e to the negative infinity, and e to the negative x decays like crazy as t goes to infinity. So irrespective of what this integral from 0 to infinity of f of tau d tau turns out to be, because of this exponential, because nothing decays like an exponential, everything will go to 0 at the upper bound. At the lower bound, we have integral from 0 to 0. By the fundamental theorem of calculus, that is 0. Brilliantly 0. So everything is just gone away. We don't need to worry about that anymore. Now here we have integral from 0 to infinity, e to the negative st over s. And now using Leibniz rule of differentiating under integral sign, since the argument contains no functions of t, everything will go to 0, plus f of the upper bound times derivative of the upper bound with respect to time, minus f of lower bound and derivative with respect to time of the lower bound. That's the Leibniz rule of differentiating under the integral sign. And we still have a dt, so don't forget that. Integral from 0 to infinity, e to the negative st. Take the 1 over s outside. Forget the 0. dt over dt is 1. So f of t. Derivative of 0, which is a constant, will make the entire thing go to 0. We just have this. And what is this? The Laplace transform of f of t with respect to s, because that was the output. The t is the input, S is the output, which we can denote as capital F of S over S. That is precisely integral from 0 to t f of tau d tau, but the Laplace of that. We have this nice formula. So I hope you enjoyed this video, guys. Please like, share and subscribe to my channel. Recommend my channel in the math community to your math friends or whatever. And in the meantime, stay home, stay safe, keep doing math, and peace out.